Yes, we can see it and we can hear you.
Great. I'm just going to switch which screen it's on. Can you still see that, or is it the wrong screen?
We can still see it. So now we actually see your kind of presenter view where we see two.
Oh, I'll stop the share and do it again. Sorry about that.
So Luke, I'll give you a 2-minute warning.
Okay, perfect. Okay, so for the next sort of 10 minutes or so, and I may have been over ambitious with my slides, I'm going to talk to you about the work we've been doing on developing self-assembled distance tunable floating membranes as a sample system for the wider neutron reflectometry user community. So the majority of the work I'm going to talk about today is the DPhil work of Laura John, who's a joint student between myself at ISIS and Mark Sampson and Gail Preston at the University of Oxford. The work she's been doing follows on from some work I did in collaboration with all these people here. Towards the end of the talk, I'm going to talk about the application of the self-assembled floating membrane system to study the barrel assembly machinery, which was done in collaboration with Timothy Knowles at the University of Birmingham. And Stephen Hall, who was at the University of Birmingham, is now an instrument scientist at ISIS. So it's been a great conference so far. I've really enjoyed the talks, and you'll see a lot of examples of lipid monolayers and supported lipid bilayers coming up as example model biological membrane systems used in neutron reflectometry and X-ray reflectometry studies at conferences like this and other similar scattering conferences. And that's because these sample systems are incredibly robust and give you a precise structural understanding of membrane biochemistry. Now, one of the great things about, say, supported lipid bilayers, which is really one of my favorite sample systems to work on as an instrument scientist, is that they self-assemble onto partially anionic surfaces. So silicon dioxide surfaces, quartz surfaces, which is silicon dioxide, mica surfaces, and sapphire surfaces. And in fact, they're so easy to assemble, we get the students of the ISIS neutron training course to assemble a DMPC bilayer and analyze it on one of our older reflectometers in an 8-hour practical. One of the disadvantages of supported lipid bilayers is their close proximity of the inner head group region to the bulk surface. So over the years, there's been a series of sample systems have been developed which aim to use the beneficial aspect of studying planar bilayers at the solid liquid interface, such as the amenability to structural and biophysical analysis techniques to give precision molecular level information, but which removes some of the disadvantages of having your planar bilayer in close proximity to the bulk solution. So examples include polymer cushion membranes, which there was an example of earlier, tethered membranes, which can either be protein or lipid tethered membranes. There's been a lot of work in this area. Now, the sample system that I'm particularly interested in is the floating supported bilayer. So this system has been developed and studied extensively at the ILL in Grenoble as a double membrane system where you have a supported lipid bilayer on a surface and then a floating membrane above this. And the type of system that we've developed at the ISIS facility is what I call the Rosa Hughes system, where you have a grafted SAM material on a gold or silicon surface, and you deposit a floating membrane onto this using Langmuir-Blodgett Langmuir-Schaefer deposition, so layer by layer deposition. Now these membranes, the floating supported membranes, float about 2 nanometers away from your SAM material due to sort of a extended DLVO-like forces, so long-range attractive van der Waals forces and short-range, which attract the membrane to the bulk surface, and short-range repulsive fluctuation, hydration, and electrostatic forces. So I came into studying floating supported membranes through the development of model bacterial surfaces. And when we started to deploy those surfaces to the user community, I was stuck doing this process really for a lot of my life. So it's layer by layer deposition of the individual leaflets of the membrane. And so to start to move this sample system forward, we thought, well, we need to create a floating version of the floating membrane sample system, which self-assembles like a supported lipid bilayer from a vesicle suspension, but which allows us to include integral membrane proteins and fluid phase bilayers, which are difficult to assemble by Langmuir-Blodgett Langmuir-Schaefer deposition, and which stops us having to do this, this very long and very technically challenging sample preparation. So when thinking about how we wanted to develop our self-assembled floating supporting membrane system, I spoke to my colleagues Max Skoda ISIS and my collaborator Martin Askavoutis at the Vilnius Technical Institute, and both of them mentioned a particular type of SAM that you can graft onto a gold surface, and these are called OEG SAMs, oligoethylene glycol self-assembled monolayers. And what they are is a file group attached to gold, a small aliphatic chain, and on top of this, a polyethylene glycol chain. And these particular SAM systems have gained a lot of interest in the literature for their role in non-stick surfaces. So if you coat a gold surface with an OEG SAM, proteins, for example, can't foul the surface because the SAM is so hydrophilic that you get a layer of gel water on the surface, which prevents a close approach and binding of any fouling material. So we thought, well, that's great. If we have these SAMs, that will stop our membrane from coming too close to the surface as having surface adhesion. But we also wanted to promote the rupture of vesicles onto these SAM surfaces. So we used an OEG SAM with a terminal carboxyl group, which mimics the partial anionic nature of the surfaces that are known to be good for rupturing phospholipid vesicles. So silicon dioxide, sapphire, and mica. So one of the first things we did is Laura ran some MD simulations, and I'm going to show a few MD simulations in this talk. And I should say I'm not an expert in MD simulations. I can tell you what the results were, but if you have any specific technical questions, you should email me and I'll put you in touch with Mark or Laura. And the first thing we did is we looked at the density profile of water around this SAM surface, and you can see, much like the OEG SAMs without the terminal carboxyl group, we get this oscillating density profile of water above our SAM, both in calcium and sodium, and that's going to become important later on, which tells us that, yes, we do have a kind of bound gel-like water layer above our surface. And so next we looked at self-assembling a floating membrane onto these surfaces. So this is some neutron reflectometry data from the OSPEC reflectometer. Here you can see NR data for the SAM on its own, the SAM in the presence of phospholipid vesicles, where you can see smearing of the NR data showing us that the vesicles bound to the bulk interface or bound to the SAM surface. And then after heat shock, you can see the formation of the floating membrane adjacent to the SAM-coated gold surface. And you can see we have around a 15 angstrom water gap between our SAM surface and between our outer SAM surface and our inner membrane surface. Now that was really good because that showed us that we could assemble these systems, and that though we didn't get a 2 nanometer water gap, which is what we were hoping, we did get a good water interlayer between the membrane and the SAM surface. But the next thing that we discovered was very, very interesting. Here's one of our self-assembled floating supporting membranes. This is a POPC, POPS, PIP-free, so quite a complex phospholipid mixture. And we always deposited our self-assembled membranes in the presence of 2 millimolar calcium, and that's because it promoted vesicle rupture onto our SAM surface. If we remove the divalent cations using EDTA sequestration, what we found was our membrane moved to quite a long distance away from the bulk surface. And you can see as it moves away from the bulk surface, its fluctuational amplitude increases, which is why you see this Gaussian broadening of the membrane density profile. If we then took the same membrane and put it back into 200 millimolar sodium chloride, the membrane would move to an intermediate distance relative to the SAM surface. So it wouldn't go back to its original position, but it would move closer to the SAM interface. If we then put the membrane back into calcium, it would move exactly back to its original position, which is with a 15 angstrom water gap between the SAM and the membrane, with no loss of bilayer coverage. So what we found was that we had a completely reversible, tunable, self-assembled membrane protein system. And so here's the neutron reflectometry data for these systems under the different electrolytic conditions. And here you can see the scattering length density profiles. And I should say, each of these data sets, the only difference between them was the only difference in the fitting between them was the thickness of the water layer and the roughness of the membrane. We created self-assembled floating supported membranes from a large variety of using a large variety of different phospholipid mixtures. So we created membranes composed of just POPC, 8-to-2 POPC, POPS, so a more anionic mixture, 7-to-2-to-1 POPC, POPS, PIP-free, so a much more anionic mixture. And then we even moved up to a very, very complex phospholipid and sterile membranes. And what we found was in each case, for each of our membrane samples, that if we that in calcium, the membrane was at its closest approach to the SAM surface. In EDTA, it was at its furthest approach. And in sodium chloride, it was at an intermediate distance. But what we also found was that if we increase the anionic nature of the membranes, the distances in sodium and EDTA got larger. And so that showed us that one of the driving forces behind this process is clearly an electrostatic effect. So using a series of molecular dynamics simulations, we tried to look at what were the underlying mechanisms of this membrane movement. And so one of the things we particularly wanted to look at is, we know that we have a lot of ionizable groups on both our SAM surface and our membranes. We wanted to look at how ions bind, how comparatively divalent cations, calcium, and monovalent ions, sodium, bind to those groups. And so this is our sort of most striking result from the MD simulations of this. This is a coarse grain model of the water interlayer between the bilayer and the SAM. And what we can show is that in the presence of calcium, due to the ionizable groups on the both the SAM surface and the phosphates and amines and so on in the membrane, because this was a mixture of POPC, POPS, we see an accumulation of divalent cations on the water interlayer region, which is clearly creating a bridging effect between the membrane and the surface. So we have an anionic surface, we have an anionic membrane, we have an accumulation of divalent cations in the area in between, and clearly that's drawing those two surfaces together. When we study the same thing in the presence of sodium, we see much weaker binding to that region, so much less bridging. And you can imagine when we have no ions in the system, you've got strong surface potentials on both the SAM and the membrane, which is causing a larger separation. So then we started to look at how we could tune the distance of the floating membrane to from the surface to our experimental conditions. And we found that if we mixed sodium and calcium together, we could get intermediate distances of the membrane from the SAM surface that were different from the membrane just in sodium or the membrane just in calcium. So we could use a mixture of ions around physiological conditions as a tuning mechanism. Okay, so I'm just going to start to talk about membrane proteins as I begin to finish off the talk. So recently we've been looking at tethered bilayers composed of hexahistidine tagged proteins bound to SAMs on gold surfaces, which we then wrap a membrane, which we then add a membrane to, which spans the region between the individual membrane proteins. So this kind of assembly process. This is a protein tethered membrane. And recently we've been studying the barrel assembly machinery, which is a large protein complex which assembles other proteins into bacterial membranes. And we were able to show that we could get a pretty good assembly of these systems onto a gold surface using neutron reflectometry. Recently, we found that we can get similar results by assembling these proteolipid membranes onto our OEG SAM surfaces with a single step vesicle rupture route. And so you end up with neutron reflectometry data like this, with a composite protein and lipid membrane, which we can convert into a volume fraction profile, and we can reveal the relative distribution of the membrane protein and the lipids and the water in our complex proteolipid membrane. Much like our lipid-only membranes, we can tune the distance of our proteolipid membrane from the surface using changes in the solution electrostatic conditions. So this is an extreme case with going from 2 millimolar EDTA in a close approach to 2 millimolar calcium, close approach, 1 millimolar EDTA, large approach, and then going back to 2 millimolar calcium again, showing we can reverse the distance changes. But we're also able to show
roughly 1 minute left, Luke.
Brilliant. Yeah, I just on my last slide.
Okay, great.
So we were also able to show that we could fine tune the distance of the proteolipid complex from the surface in the same way that we did with the phospholipid only self-assembled floating membranes. Okay, so just to conclude, we've obviously developed this self-assembled floating membrane system, which means that we can much more easily study floating membranes with fluid phase phospholipids and integral membrane proteins. Divalent cations are key to the stability of this system. We've been able to transfer this system we've been able to study this system not only by neutron reflectometry, but also by QCND and ATR FTIR. And if you want to discuss this some more with me, please find me in Gathertown or please email me. Okay, thank you very much.